Welcome back everyone, and today I'd like to begin our first major focus on organic chemistry, and that's going to be acids and bases. What I would like to begin with is Bronsted-Lowry acids and bases, and you should be familiar with this from high school chemistry or general chemistry, but if you aren't, then I took the liberty of writing down the definitions over here. So basically, before I begin to talk about these definitions, as we can recall, the old Arrhenius definition of acids and bases wasn't a very accurate representation of what acids and bases are. The Bronsted-Lowry acid and base definition is a lot more universal, I would say. And as we can see over here, Bronsted-Lowry acid is a proton donor and a Bronsted-Lowry base is a proton acceptor. And if that quite doesn't ring a bell to you, hopefully this following example will refresh that memory. So here I have a reaction written down where I have hydrochloric acid with water and then a chlorine ion and a hydronium ion. So what I'd like to do is first kind of begin practicing how to identify Bronsted-Lowry acids and bases. So in this example, the best way I like to think about it is I see that the HCl and the Cl minus are very common. The only difference between them is that this has a hydrogen and this doesn't. And what does that tell me? That tells me that this lost a hydrogen in order to become one. So in another sense, it was a donor. So this donated its proton to become a Cl minus. So I automatically know that this is going to be my acid. And conversely, if I look over here, the only difference between water and the hydronium ion is that extra hydrogen that this picks up. And what I can basically think about is that this basically accepted a proton to get that extra hydrogen. So I automatically know that this will be our base. Now, what about these two things? As you can recall, acids and bases like to hang out in pairs, and we call the respective acid-base pairs conjugate acid-base pairs. So in this case, I know that the Cl minus will be our conjugate base, which I'm going to abbreviate Cb, and this will be our conjugate acid. Now, if you're not quite familiar with how I got the conjugate base and the conjugate acid, a good way of thinking about it is that the conjugate base is what remains. So here, I'll write that down right over here. The Cb I abbreviated again as the conjugate base, is what we get when an acid is deprotonated. So deprotonated as in losing a proton. And conversely, the conjugate acid is what we get when a base is protonated, so it gains a proton. So an even easier way that I like to use to remember that is, I know this is my acid, and if this is my acid, whatever this is has to be the opposite, so it has to be the conjugate base. And how I recall that these two are very similar, except the fact that this has an extra hydrogen, and we know this is our base. This will be the exact opposite. It will be our conjugate acid. Now, typically in organic chemistry, you're not really going to see HCl and H2O and Cl minus and H3O plus like that. You're typically going to see something like this, where we have water even over here represented like this, and kind of the OH minus on the side over here, and then we also have an organic compound there. So we should also be able to recognize Bronsted-Lowry acids and bases that way as well. So in this example, once again, I notice that these are very similar, except the fact that this has a hydrogen and this doesn't, which means that this gained a hydrogen, so therefore it accepted one. So this has to be my base. And then if this is my base, its opposite pair has to be the conjugate acid. And now in this case, I notice that this lost a hydrogen, so therefore this was or is our acid, because it is a proton donor to get this. And this, if this is our acid, then this has to be our conjugate base. Remember, it has to be the opposite. So I hope these two examples kind of helped refresh our memory of how to identify Bronsted-Lowry acids and bases. And what I'd like to mostly focus our attention on in this video is the acid-base reaction mechanism. And as we have discussed before in the review, organic chemistry is all about reaction mechanisms, and this is typically the reaction mechanism that you're probably going to see first in organic chemistry. And now remember, when we talk about reaction mechanisms, these arrows do now indicate the movement of electrons. So what's happening over here? Well, before we can understand what exactly is happening over here, I think it would be beneficial if we did the exact same thing as before and identify what our acids and bases are. So over here we have the OH and water. The only difference is this has an extra hydrogen, so therefore this had to accept a proton to get this, so this has to be our base, which means that its pair has to be the conjugate acid. And then automatically we know that this over here is going to become our acid, and this will be our conjugate base. And now what I'd particularly like to specifically talk about is these curved arrows over here and why I have them specifically here. Well, in an acid-base reaction mechanism, the base abstracts a proton, so I'll just denote that as a positive charge, meaning proton. Well, here I'll do a P+, abstracts a proton from the acid. And this acid, once it's been abstracted, so once hydrogen from the acid has been abstracted by the base, there's always going to be an extra arrow where these electrons are kicked off over here once this proton has been abstracted. That's always going to be the case. An acid-base reaction mechanism like this will always have two curved arrows, no more, no less. So once again, the base abstracts the proton, and then these electrons get kicked off over here. So as you can see, the end result is that this now gains a hydrogen, becoming water, and now this electron is kicked off over here, giving the oxygen 3 lone pairs, which gives us that negative formal charge. So yes, the base abstracts the proton, and then the electrons from the bond with the proton are kicked off to the neighbor. That's basically what it is. So now that we know that, I'd like to do an example. So I guess I'll start off with this first example over here. So for the following acid-base reactions, draw the mechanism and label the acid base, the conjugate acid, and the conjugate base. So the first thing I'd like to do is label this. So once again, I notice that this has a hydrogen and this has one that's lost. So what does that tell me? This has to be our acid. This has to be our conjugate base. And automatically by default, I hope you've picked this up by now, this has to be our base. This has to be our conjugate acid. So if you figured out what one thing is, you've automatically pretty much figured out everything else. So now that we've done the first part of the question, let's draw the mechanism, which is this curved arrow notation. So the mechanism says that the base abstracts a proton from the acid, like that, and then that these electrons are kicked off over here. And that's exactly how we get this negative formal charge over here without the hydrogen, and how we get a hydrogen over here from there. So it should all make sense that way. And now I hope that this is pretty clear. So what I'd encourage you guys to do is pause the video and work on this bottom example, and then unpause the video and see if you got it right. So I'll let you do that now. And I guess we're back, and hopefully I hope you guys at least try to attempt the problem, and let's see what we get. So as I can see over here, the difference here, now this example is kind of tricky. These two are very similar, except I don't see any hydrogens anywhere. But you should remember that in bond line structures, we never show the hydrogens. They're never explicitly shown. What actually is happening over here is that one of the hydrogens from this carbon is going to be shown like that. And what happens is, now it should be more clear that this has that hydrogen and this is lacking it. So therefore, this should be our acid, and this should be our conjugate base. And then by default, this has to be our base. This has to be our conjugate acid. So we've done the first part of the question. Now the mechanism should be very simple and straightforward. So what this base is going to do is it's going to abstract a proton. So it's going to essentially deprotonate the acid. And now this is going to kick off over here. And once these electrons kick off over here, that's how we get that negative formal charge, because there's actually a lone pair now right over there that I guess wasn't being shown before. So sometimes it can be a little tricky in identifying your hydrogens, but always remember, bond line structures never show hydrogens, but they're there, so make sure you never forget that. So I hope these two examples made this pretty straightforward. And now I'd like to do one last extra example, and this example is kind of a little different. So I guess let's see what this example says. Identify the acid, the base, and draw the mechanism and determine the products. So this example is kind of different in the sense that we don't have the products. So we're asked to identify the acid and base and then draw the mechanism and determine the products. So how am I going to identify what the acid and the base is here? Well, what do we know about bases from our general chemistry in high school? We know that bases have that OH group. So I see an OH group right there. So that gives me a good hint that this indeed will be our base, and this will have to be our acid. So I've done that part of the question. Now, don't get too confused with these cations. So notice that this is actually an Li plus and an OH minus. We don't typically care about cations because they are just spectator ions in solution. There's very few rare cases where cations matter, but typically they don't. And if they do ever matter, they'll probably tell you. But for the most part, don't really worry about cations. We don't really care about them. We care more about the electrons. So I guess it's better if we redraw this right over here like this. And now this is just basically this. Now how are we going to determine the products? We know this is our acid, and we know this is our base. So how are we going to identify the products? Well, first I think it's good that we should draw the mechanism. So we know that the base is going to abstract the proton from the acid, deprotonating it, and these electrons are going to kick off over here. So that automatically should tell you what the products are, because what's happening is this base is taking this extra hydrogen. So what is it going to become? Well, it's just going to become water. So that's one of our products. And then the other product, now I hope it's pretty clear, is basically just going to be this same thing, because we didn't really do anything on that side. But what happens is these electrons now kick off, so instead of having two lone pairs, we're going to have an extra lone pair. And remember that this is going to give us that negative formal charge. So those are indeed our products. And if we wanted to even identify the conjugate base and the conjugate acid, if I know this is my acid, and these two are very similar except in the fact that this lacks a hydrogen and this doesn't, we automatically know this will be our conjugate base, and this should be our conjugate acid. So I hope that makes things a little bit easier. And that's it for this video. And in the next video, what I'd like to do is kind of get into Bronsted-Lowry acidity and looking at the quantitative and qualitative perspectives that we use to identify what is more acidic or basic. So that does it for today's video. If you have any questions, concerns, comments, my email is going to be in the description down below as always. And don't forget to rate, comment, and subscribe. Thank you.